Assalamu alaikum everybody. Welcome to our lecture number 10 for the course Introduction to Artificial Intelligence. This lecture is titled Learning from Examples number 2, where we shall continue from the subject we started in the last lecture. And here is the outline of this lecture. We will discuss about learning agents generally, and then we look at the forms of learning or paradigms of learning as they are called. Then we narrow down specifically to supervised learning. This is what we shall be learning in this course, and more particularly a type of supervised learning called classification. Now there are many techniques for classification, and in this lecture we shall look at one of them, which is learning decision trees. Sometimes it is called decision trees for short. So we'll look at the representation of decision trees, and then how to induce decision trees from examples. Right, so this is basically the target for this lecture. Let's start with learning agents. We have learned a number of agents so far in this course, as they were generally described from chapter 2. Now, the most important of these agents is the one that can learn from its experience, and that is what is called learning agent. Okay, so a learning agent is one that modifies its components to improve its overall performance based on the feedback from its previous experience. Okay, we shall look at these different components of a learning agent in the next slide. So a learning agent has four main components, as can be seen in this diagram. And here we shall just summarize the functions of each of these. For the details, I refer you back to chapter 2, where actually this type of agent was also explained in more detail. So the first component we have here is called the critique. The critique is the component that actually observe the performance of the agent against performance standards. Now, these performance standards are outside the agent itself, of course, and based on its observation, it will send feedback to another component, which is called the learning agent. So the critique tells the learning agent how well the agent is doing with respect to a fixed performance standard, whether it is doing good or not so good. And then we have the learning element. This, together with the performance element, are actually the main components that are concerned with the learning. So the learning element, it uses the feedback from the critic to determine how the performance element should be modified to do better in the future. Okay, yeah, so this is basically the component that is doing the learning. Based on the feedback it receives, it will decide, okay, next time this is the best way to handle it so that we can achieve better performance, and it will communicate the changes needed to the performance element. The performance element is basically the one doing the action. In fact, it was what we previously considered to be the entire agent. It takes percepts, from the sensors, and then it does the action by invoking the actuators. Now, so in the case of a learning agent, in addition to just the input from the passets, it can also receive inputs from the learning element. Okay, so based on this, it will do the action. We will also explain in a moment that another source of the input is the problem generator. Alright, so it receives input from all of these, and then it will decide the action to take. So what is the problem generator? The point is, left on its own, the performance element will always try to achieve the best outcome so that it will improve its performance measure. Alright, but sometimes it is good to actually deviate from the norm and try something different. Maybe that different path may lead us to learn something new. And this is the idea of this problem generator. The problem generator is responsible for suggesting actions that will lead to new and informative experiences. So it will guide the performance element. Try this option and see how it goes. Maybe that will enable you to learn new, better ways than what you already know. Okay, this is the idea of the problem generator. So generally, the agents that are of this form, learning agent, they have this kind of components. Yeah, so this in brief is basically what learning agents consist of. Next, we look at why learning agents actually. Isn't it possible for the AI programmer to build the knowledge into the agent directly? Why does it have to learn later on in its life? Well, there are very cogent reasons actually for having learning agents. These are some of the reasons. First, the designers of the agent cannot actually anticipate all possible situations that the agent may find itself in. Imagine the robot that was sent to Mars by NASA. The designers couldn't have anticipate all the kind of situation it will find itself there in the space. Okay, so in that case, it's actually better to design the agent so that it can learn and explore its environment on its own. Another example is the agents that are designed to navigate mazes. They must learn on their own the layout of each maze they encounter, because the programmer cannot, of course, anticipate all the possible mazes. Okay, and similarly, if you think about self-driving cars, as we discussed at the beginning of this course, the one that pass through the desert to reach from one point to another point, encountering all kinds of environments and being able to successfully pass through those environments. It can only do this, of course, if it is learning as it goes along. The designers cannot possibly build in all the knowledge it needs at the design stage. So this is one reason. Another reason is the designers cannot also anticipate changes over time. Maybe they know the situation now, but as time goes on, things are definitely going to change. Imagine, for example, a program designed to predict tomorrow's stock market prices. Clearly, stock market environment is one of the volatile environments that you can have. that can change from boom to bust, as it is called, at any time. So if you are designing an AI that will handle that kind of environment, you must make sure it can actually adapt with the changing situation over time. All right. And another reason is sometimes human programmers really have no idea how to program a certain solution on them by themselves. A good example is recognition programs. So for example, most people are good at recognizing the faces of family members, but even the best programmers are unable to program a computer to accomplish that task, except by using learning algorithms. So learning algorithms is really the only way to learn about recognition, whether of faces or of handwriting or voice recognition and so on. You cannot anticipate, for example, the type of voice from each and every individual in the world that Alexa will encounter, or Siri. Okay, so you have to make the agent to be able to actually learn based on its interaction with its user, how that particular user pronounce words, and be able to adapt and be able to serve that particular user. So these are some of the reasons why learning agents are very important. Okay, this is related actually to the very important subject of AI, which is called machine learning. Okay, machine learning is one of the most important and fast growing aspects of AI, and some of the things we are going to learn in this lecture and the next are actually related to machine learning. Okay, but first let's look at the forms of machine learning. There are three main types of machine learning. The first one is called supervised learning, and it's actually the one we shall be concentrating on in this course. So in supervised learning, the agent is actually taught this A maps to this B, this C maps to this F, and so on, using training data. So the agent observes some example input-output pairs. Okay, a set of input-output pairs, which is called training data, and then based on this, it learns the relationship between the input and the output by forming a kind of function that will map a given input to a given output. So once it forms this function, this is what we have here. For example, it says given D, a certain domain consisting of xi and yi, the supervised learning is designed to train the AI system to relate the xi's to yi's. In other words, to be able to generate some kind of function, or what is called a model, that will generate the yi given the xi. Okay, so this is the idea. So once it learns and generates this model, then next time it encounters a different value, not necessarily in the training data, a different x value, it should automatically be able to map it to its corresponding output using the function or the model that it has generated from the training session. We shall discuss in detail about this in this course, and actually the decision tree that we are going to learn in this lecture is an example of this supervised learning. Okay, but before we get back to that, let's talk about the other two major types of machine learning. We have unsupervised learning. Now, in unsupervised learning, the agent is provided with just the input data, no output at all, just the input data, and it is required to learn on its own the hidden structure of the data. Okay, so it is given a data in a certain domain, and we expect it to learn and formulate a kind of function f that, given certain value xi, it will be able to again generate the output. So, but this time it is doing everything on its own without being guided by a training data. It learns and be able to structure this, find the structure of this data or this model. It finds this model on its own. Okay, the most common unsupervised learning is what is called clustering. Clustering means detecting potentially useful clusters from input examples. All right. For example, a taxi agent might gradually develop the concept of good traffic days and bad traffic days without any human trying to teach it using some kind of training data. No, on its own, just by experience, it may be able to, if it has the capability of unsupervised learning, it will be able to identify on its own which days are good for traffic and which days are bad. Okay, this is just an example. Now, the third type of learning is called reinforcement learning. So this is somewhat in between the two forms of learning that we have already discussed. In reinforcement learning, yes, the agent is not going to be trained. So again, there is no training involved. But also, we don't want to leave the agent completely on its own. Rather, what is done is that the agent is given a reward if it does good, and it's given some kind of punishment, okay, if it does bad. So based on this kind of input from maybe a human user, the agent will gradually know what action are good to take and what action are not good to take. Okay, for example, the lack of a tip at the end of the journey gives the taxi agent an indication that it did something wrong. Okay, or if it got a tip, it should indicate that it did something good. Now, of course, it is up to the agent to decide exactly what went wrong or what went good, so that it capitalizes on that in the next time. Nobody is going to tell it, this is the action that you did that makes you to deserve this reward or to be punished based on that. It is up to the agent to decide what actually causes the reward or the punishment it is getting. So these are the three main types of learning paradigm, as they are called. And as I said, we shall be concentrating on the first one here, the supervised learning. Okay, so this nice diagram summarizes the three forms of learning. Okay, So as you can see, the supervised one, it has labeled data where the input and output are clearly mapped in the training data. So this input will have this label as its output, and so on. It is given therefore direct feedback. And the objective then after the training is for it to be able to predict the output from new set of data, which is called the test data, okay, or from new features as they are called. Unsupervised learning, on the other hand, there are no labels, no feedback. Okay, simply take this data and find the hidden structure that is inside. All right, and the last one, reinforcement learning, basically is based on reward system, where the agent is either rewarded or not rewarded, and based on that it will use that as input to improve on its experience. Okay, so but let us now concentrate on the first type of learning, which is called supervised learning. So the task of supervised learning, as we said, is giving a training set of n example input-output pairs. x1 is mapped to y1, x2 is mapped to y2, and so on. The idea is where, of course, yj was generated by an unknown function. So the system doesn't know which function actually maps x to y, or the x's to the y's. It doesn't know. And the target is for the system to discover a function h that approximates the true function of f. Okay, so it doesn't have to find f 100% correct. Okay, the idea is to approximate. So find an approximate function h, which is actually called hypothesis, that will try to generalize and say, okay, for this input, this is supposed to be the output. Okay, x and y can be any data type. We have discussed different types of data in the last lecture: ordinal, categorical, numerical, and so on. So it doesn't have to be numeric, it could be any type. And as I said, the function h is called the hypothesis. So the objective in supervised learning is to find the hypothesis. Sometimes it is called the model. And therefore learning in this case is actually a search through the space of possible hypotheses. There is a space of hypotheses, so many different hypotheses, and the objective of supervised learning is to identify one of them that can actually structure this data, so that given an x, it can correctly map the corresponding y. Okay, and this should of course work even with new examples that are outside the training set. To measure the accuracy of hypothesis, we give it a test set. Okay, so a set of examples that are different from the training set, and we want to see if it will map them correctly. And we say that a hypothesis generalizes well if it correctly predicts the value of y for each novel example. All right. When the output y is of a finite set of values. For example, sunny, cloudy, or rainy. Then the learning problem in this case is called classification. Okay, so classification is a supervised learning where a set of attributes are mapped to finite set of values. If in fact there are only two possible output values, then it is called Boolean classification or binary classification. Now, if y is a number, such as tomorrow's temperature, then the learning problem is actually called regression. So we have classification and regression. Classification is when the output are a fixed finite set of values, whereas if the output is going to be some real number, it is called regression. Yeah. So technically, solving a regression problem is actually finding conditional expectation or average value of y, because actually you cannot in that case find the exact value of y. It is almost impossible to find an exact mapping from x to y if we are dealing with real numbers, for example. Okay, let us give a more formal definition of classification. Alright, given a collection of records, which we normally call training set, where each record contains a set of attributes, and one of the attributes is the class. The idea of classification is to find a model for the class attribute as a function of the values of the other attributes. So the goal is previously unseen records should be assigned a class as accurately as possible. This is basically what classification is about. And a test set is used to determine the accuracy of the model. Usually the given data set is divided into training and test sets, with training set used to build the model and the test set is used to validate it. I'll show you an example in the next slide. So here we have a collection of about 15 records, 15 data records, and they are grouped into two sets: training set and the test set. Actually, this is how it is normally done. You group your data records into two, and usually the training set should be larger, in the ratio, for example, of 70 to 30 or even 80 to 20%. So you train your classifier using the training set, and then you test it using the test set. So here, as you can see, each record consists of attributes: attribute 1, attribute 2, attribute 3, and one of the attributes is a class. In this case, the class is Boolean, simply two values, either no or yes. Okay, so you're gonna train your classifier using some algorithm, and we're gonna learn at least two algorithms in this course, or two techniques. In this lecture we will see decision tree, and then in the next lecture we shall see neural network. So the idea is for the algorithm, the learning algorithm, to take the examples here and use them to build a model or to learn a model. So we have a model, and then now we use the test set to validate the model. Okay. okay, and see whether it will be correct. This is the idea. There are many applications of classification tasks. Here we list a few of them. One is predicting tumor cells as benign or malignant. This is testing for whether someone has a cancer or not. So if a cell is benign, then it is not a real cancer. But if it is malignant, then it is very serious. And there are AI systems that are developed to do this using images from the cells, for example. So a lot of images are used to train the classifier, and then based on that, if it is given another image, it will be able to determine whether the cell is actually benign or malignant. Another example is classifying credit card transactions as legitimate or fraudulent, given the transaction information. So again, you train the classifier using several examples to teach it when to consider a transaction to be legitimate and when to consider it to be fraudulent. Okay. Another example is classifying email messages as spam or not spam. If you are using Gmail, for example, I'm sure you will have seen that they have a very effective spam filter that automatically moves almost 100% of spam messages to the spam folder and allow only the legitimate messages to be in your inbox. So this is another example of classification. The last example I'm giving here is categorizing news stories into different types of news. It could be about financial news, usually important for business people. Could be about weather, entertainment, sports, politics, and so on. So giving a text of the news, or maybe even just the headline, let the classifier determine what category it belongs to, and maybe move it to a different folder accordingly. Now there are many techniques for handling classifications. Here I will just list some of them, but actually we will only concentrate on two of them, as I will explain in a moment. So you have learning decision trees as one example of classification technique. This one we are going to study immediately, actually, in this lecture. You have what is called rule-based methods, memory-based reasoning, neural networks. So this again we are going to study, but in the next lecture. Naive Bayes and Bayesian belief networks are another examples of classification techniques. Another popular one is support vector machines. Okay, so these are some of the techniques that are used in classification. Okay, so let us start looking at the first one, therefore, learning decision trees, as the technique we shall learn in this lecture. Learning decision trees. Decision tree induction, which means learning from examples using decision tree, is one of the simplest and yet most successful forms of machine learning. We're going to first describe the representation, the hypothesis space, and then show how to learn a good hypothesis. Okay, so the representation first. A decision tree represents a function that takes as input a vector of attribute values and return a decision, usually a single output value. The input and output values can be discrete or continuous. We shall be concentrating on problems where the inputs have discrete values and the output has exactly two possible values, yes or no. In other words, we will be concerned with Boolean classification in this lecture, where each example input will be classified as true or positive, or as false or negative. Okay. But first, how does decision tree work? So a decision tree reaches a decision by performing a sequence of tests. As you can see in this example, each node in the tree involve a test. Say each internal node in the tree corresponds to a test of the value of one of the input attributes, call it AI, and the branches for the node are labeled with the possible values of the attribute, so VIK. So for example here, we are first checking. The idea of this small example is to check whether a person is fit or is unfit. Okay, and the attributes being considered are his age, whether he does exercises or not, and whether he eats pizza or not. Okay, so the first thing we check in the root node here is the age. Is he aged less than 30? In other words, is he young and energetic, or is he getting old if it's greater than 30? So you can see the branches are labeled with the two possible output, yes or no. So if the answer is no, then we do the next test, which is to check whether the person does exercise or not. Okay, so if he doesn't do exercises and he is more than 30 years, we conclude that he is unfit. But if he does exercise, we conclude that he is fit. Similarly here, even though he is young, if we ask that does he eat pizza, and the answer is yes, then the conclusion is he is unfit. Otherwise he is fit. This is basically how decision trees reaches their decision, by examining a sequence of attributes in this manner. Now each leaf node in the tree specifies a value to be returned. So the leaf nodes are values of possible output. In this case there are only two outputs, whether the person is fit or unfit. Decision tree representation is actually very natural for humans, and we use it implicitly without knowing. Normally when you are going to do something, you will start asking yourself, what if this is true? Then you decide to do this or to do the other thing, and so on. In fact, many how-to manuals, like DIY manuals for repairing an item like a car, are written usually in the form of decision tree. Okay, which may stretch over several pages. Similarly, in computer terms, troubleshooting is another example that is normally done using the decision tree naturally, without even thinking. So in fact, you may not know it, but most likely you have already used decision tree in your life. For example, if you had ever called customer support service, any customer support service, for example for your bank, you will normally be directed to an auto receiving machine that will be asking you some questions. Maybe the first question is, for English press 1, for Arabic press 2, and so on. And then based on your choice, you will be directed to dial another button, and so on. So this is actually decision tree in practice. Those auto answering machines, they are actually implemented using decision tree, and they behave exactly the way decision trees work. Okay. Yeah. So we're going to take an example, this example from the book, and then we will see how decision tree is actually generated from examples. So we say in our example 1, we will build a decision tree to decide whether to wait for a table at a restaurant or not. So you came to a restaurant and you find that all tables are full. The question is, are you going to wait for a table to be free, or are you going to leave and try to find another restaurant, and so on? Okay, so this is our example. The aim is to learn a definition for the goal. The goal is will wait. So will wait be, is it going to be true or is it going to be false? And the list of attributes to be considered as input are as follows. The first attribute is alternate, meaning is there an alternative restaurant nearby? So maybe based on that question, you can decide whether to wait or not. The second one is there a bar? Meaning, is there a comfortable waiting area in the restaurant where you can wait for a table to be free? Is it weekend? Here it says Friday or Saturday, because of course the assumption is we are in the US, for example, where the authors of this book are. Our weekend here is Saturday and Friday. So anyway, the question is it a weekend? Because if it is a weekend, most likely, even if you go to another restaurant, it may also be full, because many people are likely to be out in a weekend. Another question is, are you hungry? Okay. Are there many patrons or customers in the restaurant? Alright, so the answer here is not necessarily Boolean. There are three possible answers. None, there are no customers, so that will be odd. If there are no customers at all, something is fishy. Okay, there are some customers and the restaurant is full, and the price range is something to consider. Maybe this restaurant is cheaper than alternative restaurants around. Another factor to consider is it raining outside? Because if it's raining, most likely you will not find it difficult to wait for a table to be free. Do you have a reservation or not? What type of restaurant is this? Is it a French restaurant, Italian, Thai, or a simple burger restaurant? Okay, so these are all factors to consider before you decide to wait or leave. And the last one is the estimated time to wait. So wait estimate in minutes. Is it between 0 to 10 minutes, 10 to 30 minutes, 30 to 1 hour, or is it more than an hour? So these are the factors to consider in this example to allow you to determine whether you should wait or not. And this is a possible decision tree that is generated by the authors of our book. So this is not based on learning from example. This is just the authors deciding for this tree, that this is a possible decision tree that can be used to determine whether to wait or not. So you can see it says if the patrons or customers in the restaurant, if there are none, then probably you should also leave. Maybe something is wrong with the restaurant. Okay, but if there are some, obviously you're going to have a table, because if it is not full, there is a table for you, so obviously you will wait. Okay, but if it is full, then now you have to consider the wait estimate. How long is it going to wait? How long do you have to wait to get a table? Obviously, if it's going to be more than 1 hour, probably you better leave. Okay, but if it is just between 0 to 10 minutes, probably most likely you will wait. Okay, between 10 to 30 minutes, maybe it depends on whether you are hungry or not. Or if it is more than that, then you begin to ask, are there alternate restaurants nearby? Okay, even if there are alternate restaurants, if it is a weekend, probably you will wait. If it is a weekend, probably you will wait, because you know, even if you go out, the next restaurant may also be full, because many people are eating outside. Okay, and so on and so forth. So this is a sample decision tree which is generated by our authors. Okay, but actually what we want is an algorithm that will generate this kind of tree automatically for us based on some example data. Okay, but before we get into that, yeah, it's saying please note that in this tree the attributes price and type were not used at all, so they only draw the tree based on 8 out of the 10 attributes. Yeah, so before we look at how to actually generate that tree using an algorithm or a tree similar to that, maybe even better than that, let us look at the expressiveness of decision trees. How expressive are they? Okay, so a Boolean decision tree is logically equivalent to the assertion that the goal attribute is true if and only if the input attributes satisfy one of the paths leading to a leaf node with a value true. Okay, so writing this out in propositional logic, we have the goal is true if and only if pass 1 or pass 2 or and so on will lead you to true. Okay, this is the idea. Okay, so where each path is a conjunction of attribute value tests required to follow that path. Therefore, we can say that the whole expression is equivalent to disjunctive normal form. Disjunctive because we are using or, and each of these paths is a combination of and. Okay, this is true and this is true and this is true. So if you have that, it is said to be a disjunctive normal form. Now what this means is that any function in propositional logic can actually be expressed as a decision tree. Any function in propositional logic can be expressed as that. As an example, the rightmost path in the figure we saw on the last slide, I will go to it in a moment, can be written as patrons is equal to full and weight estimate is equal to 0 to 10. Okay, let's go to that path and you see what I'm talking about. This path from patrons to this true here is basically, as you can see, the patrons is equal to true and weight estimate is 0 to 1. Okay, so that this path can be represented in propositional logic as what we saw there. Okay, so equivalently, any logical expression can be actually represented as one of the paths in a decision tree. Okay. Now, for a wide variety of problems, the decision tree format will yield a nice, concise result. Okay, so it's very much applicable. However, some functions cannot be represented concisely using decision trees. So it means it works for some problems, but it doesn't work for some others. Okay, for example, the majority function, which returns true if and only if more than half of the inputs are true, will require an exponentially large decision tree. If you try to draw or to represent this function as a decision tree, the decision tree is going to be prohibitively large. Okay, so generally, if we consider the set of Boolean functions of n attributes, how many different functions do you think there are in this set? This will help us to see how feasible it is to generate, or rather to represent, how feasible it is to represent problems involving n attributes using the decision tree. How many different functions are there in this set? Okay, this is actually just the number of different truth tables that can be written down. Okay, because the function is basically defined by its truth table. And a truth table over n attributes has 2 to the power n rows, one for each combination of the values of the attributes. Okay, 2 to the power n rows. Now we can consider the class column or the answer column of the table as 2 to the power n bit number that defines the function. In that case, it means that there are going to be 2 to the power n different functions. Okay, yeah. So this is actually a very huge number. So this is a huge number. For example, with just the 10 Boolean attributes that our restaurant problem has, the number of rows is going to be 2 to the power 10. Okay, and the number of possible answers that you're going to have is going to be 2 to the power 10. Well, 2 to the power 10 is 1024, and then 2 to the power 1024 is about 10 to the power 308, and this is a very, very big number. try to increase the attributes to 20, and you see how incredibly the number grows. So essentially what this says is, although you can represent any problem using decision tree, it is very, very expensive to do that, both in terms of space, but also in terms of searching, because you are basically searching an exponentially large space. So what we need actually is a more efficient way to represent decision trees, better than just normal full decision tree where we take care of all possible cases. Okay, so what we are going to do is we're going to see a heuristic algorithm that can actually help us to build a more efficient decision tree just by learning from a set of examples. So for our restaurant problem, we are going to assume we have this 12 examples. Okay, so you can see, for example, for x1, alternate is true, but bar is false. Friday, Saturday is false. Hungry is true. Patrons, some. The price in terms of $100, hundreds of dollars. It is not raining, and this particular customer has a reservation, and the type of restaurant is a French, and the estimate time is between 0 to 10. So this example says the customer decided to wait. This is the answer, and so on and so forth. So these are the examples we have. The question is, can we have an algorithm that will generate for us a more simpler tree rather than using the full decision tree for this type of data based on only these examples? And the answer is, of course, yes. Okay, so that's what we are saying here. We want a tree that is consistent with the examples and is as small as possible. So unfortunately, there is no way to efficiently search through the 2 to the power 2 to the power n trees. It is an intractable problem. However, with some simple heuristics, we can find a good approximate solution, and this is our target, that will give us a small, maybe not necessarily the smallest, but consistent tree. And the heuristic is given by a decision tree learning algorithm, which is a greedy algorithm that uses divide and conquer strategy. And here the greedy choice is to always test the most important attribute first. Test the most important attribute first. Later on we will learn how to actually find the most important attribute. Okay, so what this tree does is it divides the problem into smaller subproblems that can then be solved recursively by choosing the most important attribute first each time. So say by the most important attribute we mean the one that makes the most difference to the classification of an example. So again, we shall see this later in the lecture. So that way we hope to get the correct classification with a small number of tests, meaning that all paths in the tree will be short and the tree overall is going to be as shallow as possible. Okay, here is the decision tree learning algorithm. As you can see, it takes as input examples. So the set of examples that is going to be used for the learning or the training. Set of attributes, parent examples. Initially this is going to be empty, but as we make a recursive call, we will be passing these values. So these are the inputs, and we want the algorithm to tell us to return a tree. Return the decision tree. So this algorithm constructs decision tree based on the examples. Okay. Now there are actually 4 cases to consider in this algorithms. 2 of them are typical, and 2 of them are special cases. I will start by looking at the typical cases. So the first case is the second one here. Say if all examples have the same classification, then return the classification. So if all examples, when you consider a certain attribute, they are all true or they are all false, okay, but it doesn't have to be a true false, it could be actually an ordinal value, but the main idea is all the examples have the same output. So in that case, just return that particular classification, whether it is true or whether all of them are false. So if all of them are false, return the false. If all of them are true, return true. So this is the first typical case. The second typical case is where the examples are not all in the same class. For example, some are true and some are false. So what do you do in that case? This brings us, this is handled in this else part. So if you have a mixture of different outputs, then what you do is try to partition the examples. And you're going to partition the examples by choosing the most important attribute and use that attribute to partition the examples. We will learn later how to choose the most important attribute. Okay, but the idea is once you partition, then basically you are going to have sub branches. Okay, so you will group your examples based on the different branches possible for this particular attribute. For example, if it is a boolean, then along the yes you're going to have another branch, along the no you're going to have another branch. Okay, and then you're going to repeat this process. So this is why you see, for example, there is a recursive call here. Okay, so this allows you to now go and create another branch and so on until you meet this case here where we have the same set of classification. So in that case we just return the classification. So this is basically how the partitioning is done. Let me look at the 2 other cases that this algorithm is dealing with, and because apart from these 2 cases there are 2 others. The first one here, it says if examples is empty, then return plurality value of the parent example. Okay, so basically what we are saying here is if in some leaf, so you try to go to a branch and then you find that you have no more examples to deal with, no more examples. So it says choose true or false according to the number of positive or negative examples at the parent node. Okay, so we're going to terminate at this point based on how many or which of the 2 options are more in the parent node. So if the parent node has more false, then we will return false. Or if it has more true, then we will return true. Okay, because normally we will use the examples to decide whether we should return true or false. But it turned out here that we attempt to go to a branch, but we have no more examples to deal with. So if you have no more example, refer back to the parent. This is what this is saying, based on the plurality value of the parent. Okay, and the other case is here. So if attribute is empty, so you still have examples to deal with, but somehow no more attribute to consider. You attempt to create a branch, but there are no more attributes to use. Okay, this actually is an indication of noise in your data. This should normally not happen, but it's possible for it to happen. Okay, it means two or more examples have the same attribute but different level. Okay, it's an indication of noise in the data. So again, the solution is stop and use majority vote. Okay, so among the remaining examples that you have, if those that are true are more, you return true. If those that are false are more, you're going to return false, and so on. So this is basically the decision tree learning algorithm, but the best way to actually understand it is with the example. So we're going to continue our example with the restaurant domain to see how it works. And we're going to do that with these two attributes, patrons and type. Okay, we are trying to partition the data, first using patrons and then using type, according to the algorithm that we just discussed. Okay, so here, for example, if you concentrate here, I just cut the table because I only needed to show you how to do it based on the patrons attribute and based on the type attribute. It's not the full table. If you want the full table, you will see it in the previous slide. Okay, but the idea here is, suppose we have chosen patrons as our important attribute based on which we wish to split the examples. Okay, so obviously patrons, as you can see, it has three possible values, either some or full or none. So try to count how many of them do we have in each case, and what is the output. So let's start with none. Okay, so you can see that we have two nones, none with a value false, and also here none with a value false. Okay, so for the none branch, therefore we're gonna have two examples, and both of them are false. So this is actually good, because since both of them are false, this is going to be a leaf node, and we're going to return false. We're going to terminate this tree and return false. Okay, let's look at sum. So sum, you can see with a value true, sum with a value true, sum with a value true, and sum with a value true. So those are the four sum, and all of them are true. Okay, so we mark them here with green color to indicate that they are all true. So again, you can see that all the examples have the same output. So this is going to be a leaf node, and we're going to return true. Okay, we're going to return true for this particular leaf node. Okay, let's look at the last one. Full. Full here, however, there are two versions of the output. There are two of them with true. This is true, and where is the other one that is true? The last one here. So these two are true. So that's why you see two green here to represent the true. But there are four other fulls, 1, 2, 3, 4. And if you look, their output are all false. Okay. So therefore, in this case, we cannot have a leaf node, because we still have examples that are mixture of true and false. Okay, so we have to actually do another splitting based on another attribute. This is basically what the algorithm suggests. Okay, on the other hand, if you look at type, it turned out to be a very bad attribute to use for splitting, because in all the cases it gives us a mixture, actually equal number of false and true. For example, if you take French, we have two French, one of them is false, one of them is true. Okay, the same thing for Italian. Italian, one of them is true and one of them is false. For the Thai, there are four of them. Again, two are going to be true, two are false. And for the Burger, the same thing, two true, two false. So this is actually a very bad attribute to use, because it's not allowing you to reach a leaf node. This is the idea. Let's go through the points I have on the slide. So the above figures show that type is a very poor attribute, because it leaves us with four possible outcomes, each of which has the same number of positive and negative examples. On the other hand, patrons is a fairly important attribute, because if the value is none or some, then we can answer definitely no or and yes respectively. Okay, if the value is full, we are left with a mixed set of examples, and then we can apply another attribute to do the splitting. So this is basically how the algorithm works. You choose an attribute. We will learn, of course, how to choose an attribute in a moment that will allow you to have a better splitting. So you can see here the choice of which attribute to use actually is important, because some attributes are useless, as the type here. It didn't help us at all. But patrons has helped us, because automatically we have discarded half of the examples. We have made a conclusion and we only have half to deal with. But here we have not reached any conclusion at all. Alright.